Okay, we're live. Hey everyone, hope that round went okay for you. So, yeah, so just general thoughts about the round. I think actually the difficulty was overall pretty good this time. I think a lot of the Div 3s often have um, like the early problems A and B and so on really difficult. And so this time, A and B were definitely on the easier side, which is good. Just more problems for more people. And then C and D kind of gradually got harder. And then maybe the biggest thing was that there was a big jump between D and E. So maybe they could have, squeezed another problem in between, but it's not necessarily too bad. Looks like it dropped about 10x in terms of the number of solvers. uh, Vanilla says C was trash. Even D was easier. That's funny. Yeah, C and D were like about the same difficulty, so it makes sense that some people found D easier. This contest was a typing practice for you, wasn't it? Actually, unfortunately I messed up C, which cost me a lot of penalty. So I submitted it first around the 7-minute mark, but then got wrong answer. Took a little while to find the bug, almost 4 minutes, and then submitted it, and got AC at 10 minutes. And so that cost me a 10-minute penalty, plus like 4 extra minutes for every problem starting from C. So that was a pretty big amount. It wasn't completely typing practice. I had to, think a little bit on some variations of how to do E or F, especially. And so, yeah, it wasn't. I definitely had parts where I was just thinking and not like jumping straight into coding. A couple of people interested in E and F. Yeah, we'll definitely get to all the problems right now. I will upload on YouTube sometime after the stream. It takes a little while to process. But yeah, we'll go through all the problems, but I'll go in order from A through F just because, most people, almost everybody worked on, A, B, C, but not everyone necessarily worked on E. Okay, so sure, let's just jump right in. So for problem A, we're given an integer n, and then they explain what a permutation is. It's an array of all the numbers from 1 to n in some order, and then every number has to appear once. And we need to find a permutation of length n so that none of the permutation values match their index. So there's no index where pi equals I. And that's pretty much it. N can be between 2 and 100. Obviously for n equals 1, it's not possible. So here there's a bunch of different solutions. The main way to, I'll just make a file here. The main way to think about it is, we have some kind of permutation like this, and we just want to rearrange everything so that nothing lines up. So there are a lot of different things we can do here. What I did in particular was just to shift everything over by 1, and so I end up doing something like this. And this will always work because every value will be off by 1 from the value we're trying to avoid, so it's perfectly fine. I guess 1 is off by 1 from 6 in a sense of like if you put all the numbers in a circle. Some other options are, one example is because it's solvable for 2, because 2 is 2, 1, and then it's solvable for 3, you could do something like 2, 3, 1, right? Then you can actually build up any n using 2 and 3. So for example, for 6, we can just use a bunch of 2, right? So we just take these 2, and we take these 2, and so on. And then, for example, if we instead had 1, 2, 3, 4, 5, 6, 7, we can just break it up into 2s and 3s again. And then 2, 3, 1 would map to 6, 7, 5 here. So yeah, anyway, a lot of different solutions. This is probably the easiest one. The one thing that you want to make sure that you're not doing here that might be tempting is just reversing the array. So for example, for 6 it works, but for odd numbers like 5 it would not work because you would end up with this 3. So the implementation of this idea, super simple. You just build an array, use I+1 mod n, and then I have an output function. And this true means that I add 1 to every value before outputting. And the reason is that way I can convert 0 base numbers into 1 base numbers. A couple of people asking, I could only solve one problem or 2 problems. Is that good or bad if I'm a beginner? Yeah, definitely not bad if you're a beginner at all. I think the main advice I would give is just to focus on, not on where you are now, but just focus on learning more and improving. And that way, even if you have a bad contest, it's still a learning process, you're still improving. And so you don't have to worry too much about how you're doing right now. Okay, so that was A. Let's jump into B. So for problem B, we have n participants. Every participant picks a number, and then the winner is a participant that chose a unique number. And if there are multiple unique numbers, it's the smallest unique number. And you need to print the index of the participant who won, or determine there's no winner and then print -1. So for example, in the case of 213, it would be the participant who picked 1 because that is the smallest unique number. So the answer is 2. In the case of 2223, only the 3 is unique, so that would be person index 4, and so on. So for example, 23242, it'd be the person who picked the 3 because 2 is not unique, and so it's index 2. So really simple problem. We just need to implement what's described. I did it personally using a map. So I count the frequency of every number, and then I initialize a winner at -1, go through everybody, and if their frequency is 1, and either the winner is negative, which means it's not set yet, or our current number is less than the winner, then we replace our winner with I. And then this logic is just so that basically I want to convert 0 base to 1 base, so I want to do +1, but I don't want a +1 to -1, so I just do a little ternary condition there. So really simple problem. Yeah, let's move on to problem C. Okay, so here we have an array A, we have n integers, and they describe a process. We can choose some integer x, and we can do the following operation. Pick some segment of the sequence and remove it as long as it doesn't contain any x. And we want to get the sequence down to everything being equal. So for example, if this is our array, we choose x equals 1, then what we could do is we could remove 3, 2, and 4 with one operation, and then we can remove 2 with one operation, and we get to 1, 1. And we want to find the minimum number of operations to get to an array where everything is equal. So first thing to notice is clearly the number that we end up on should be x, because there's no way for us to remove x's. So x should be the only number remaining by the time we're done. And then if we have an array where we know where all of the x's are, then we just need to remove all the segments corresponding to not x's, right? So that immediately gives us one algorithm. The algorithm is to loop over all possible values of x, and then find where all of them are in the array, and then after that, just count the number of segments kind of stuck in between them. But this is n squared, and n is going to be up to 2 times 10 to the 5th, so that's going to be too slow. So we need to think of something a bit like, a good amount faster than that. And in this case, we can improve to either n log n or O of n, depending on how you implement it. But the main idea is, first of all, what we can do is if we have any repeated values, we can just throw them out, right? So if we have an array that looks like 1, 1, 1, 3, 3, 2, 2, 2, we can just replace this with 1, 3, 2, right? Because multiple repeated values can just be considered as one value where we'll either remove all of them at once or none of them at once. So it turns out in C++ at least, this is super easy to do. You can use this function called unique. Often you use this after sorting because let's say you want to get a list of the distinct sorted values in an array. You can sort the array and then call unique and then get that list. But you can actually call unique on a non-sorted array. What it'll do is it'll just remove all of the kind of duplicated values. So it'll only keep the first value in a range of equal values. And so the first thing I do is call unique on the array, and I just erase everything after unique to the end, and then resize, or get the size again and put it as n. And now we can think about an array where basically everything, every consecutive pair of values are different, right? And so now what we want to know is, okay, let's say we pick a certain number. Let's say we pick x equals 3 here. How many segments do we have to remove in order to get everything to equal x? Let me add a little bit more here. Okay, and so first of all, we just need to know where the x's are, right? So we have 3 of the 3's here. And so we just need to remove the 4 segments around the 3. So first of all, it's this one, and then second this one, and then this one. So here it looks like number of occurrences of x plus 1, right? Because we have 3 occurrences and then we have 4 bad segments around it. Time complexity of unique function. Unique is O of it, so you don't have to worry about that. Yeah, so it looks like this is the answer, but there are a few cases where that's not right. One example is 3, 1, 2, 1, 1, 3, where actually we only have to remove 1 segment, but number of occurrences plus 1 would actually give us 3. So we're off by 2. Basically, the reason that this can be incorrect is if one of the occurrences of x, or any of the occurrences of x, are at the ends of the array. So for example, in the case above, if we didn't have this 1, then we have this kind of ghost segment to the left of the first 3 that we don't actually need to handle, right? And so the way to adjust this is we can just do number of occurrences of x plus 1, and then minus 1 if x is the start of the array, and then minus another 1 if x is at the end of A. Oops. And so this tells us for any particular x how many segments we'll have to remove to get just x. And so then in terms of implementation, we can do this again pretty easily with just a map. So almost the same idea as B here, just to count the occurrences of everything. And then, yeah, so I just go through every value in A. I actually, repeat the same x more than once, but it's fine because I'm just going through the array once. So this particular solution is n log n. And yeah, so this is the formula that I described. Number of occurrences of A plus 1 minus 1 if A is the first element, and then minus 1 if A is the last element. How do you select x again? I joined late. So just a quick recap. So basically, first we're going to take the array. We're going to call C++ unique on the array. That's going to get rid of all of the duplicated values. So for example, for this array, it would give us 1, 3, 2. And then now that we have these duplicated values gone, then we have an array that kind of looks like this. If we pick a certain value of x, for example, x equals 3, then generally the number of segments we need to remove is the number of occurrences of x plus 1, which you can see here. But there's some special cases when x is the first element or the last element. And so this is a revised version of the formula that is fully correct. And so we don't actually we don't actually know in advance which x to pick. We just try every x, and we just do this formula. And the way we do it quickly is by having a map and then counting the occurrences of everything. Then someone asked about the erase. So unique makes the elements unique and then returns the iterator to the end of the new unique sequence. It can't actually resize your vector for you because you're only passing in begin and end. So we actually need to go in and erase everything from the point that it returns to the end. And then I also, I guess this is unnecessary, but I just reassign n here. The map here is literally just used to count how many times each number occurs in the array. Okay, looks like people generally understand that one. Let's jump into, let's take a look at problem D. So now for problem D, we need to find, we're given an integer n greater than 1. We need to find a sequence of integers a1 through ak such that every ai is strictly greater than 1. The product is n. And then also ai plus 1 is divisible by ai for every I from 1 to k minus 1. And then also we want the sequence to be as long as possible. And we're given up to 5,000 test cases. Every n is between 2 and 10 to the 10th. But also importantly, it's guaranteed that the sum of n doesn't exceed 10 to the 10th. Okay, so, and then also we need to print not only k, but we actually need to print the sequence here. Can we solve d for n less than or equal to 10 to the 18th? It turns out that yes, we could. We would have to use a better factoring algorithm. If we use Pollard row here, that would actually work here. We would still need this constraint of sum of n does not exceed 10 to the 18th. Okay, so let's try to figure out, first of all, how do we maximize k? Like, what is the best way to do this sequence? And so when we get this type of problem where we're thinking about kind of dividing up the number n into a bunch of factors that all multiply to n, if we can afford to, it's really good to think about the prime factorization of n. And in this case, given the problem, we actually do have enough time to factor n. At first glance, it seems like it's too slow because the basic algorithm to factor n would be square root n time. Square root of 10 to the 10th is 10 to the 5th, which is fine. But if we multiply that by 5,000, that would be too slow. But luckily, we have this constraint that the sum of n doesn't exceed 10 to the 10th. And so basically, if we're guaranteed that sum of ni is less than or equal to 10 to the 10th, then if we consider sum of square root of ni, it turns out we can show this is less than or equal to 10 to the 5th. And so in terms of runtime, we'd be fine to factor everything. Basically, the way you can show this is actually, let me think for a sec. Yeah, so we can just show that if we have two numbers a and b, then square root a plus square root b is oh, sorry, wait a second. This is not okay. This is not quite true. If we had 10 to the 10th ones, for example, then this is clearly bigger than 10 to the 5th. But because we have only 5,000 test cases, it turns out the worst case, so this is not true. The worst case is going to be 5,000 times square root of 10 to the 10th over 5,000. And In this case, we're actually fine because that would be 10 to the 5th times, oops, did the wrong way, times square root of 5,000. And so that would be about 7 million mods, which is fine. Yeah, basically you can show mathematically that the way to maximize this is to make all of them equal. One thing you can do is just to show that, for example, square root a plus square root b is less than or equal to 2 times the square root of their average. I believe this is true. Yeah, and this is because square root is a concave function. So yeah, this is true, and then basically we can just apply this inequality to the whole thing, and we can find that the runtime is not too bad. Yeah, so we can afford to factor every number in here. And so now we can just work with the prime factorization instead. So let's say we have a number that is 2 cubed times 3 to the 5th times 7. So we don't even need to know what the number is. We just have this factorization. And we want to find a sequence of numbers that multiply to this where each number is divisible by the number before it. So first of all, we for sure cannot make a sequence longer than 5, right? And basically, the reason for that is if the sequence is longer than 5, so let's say we have a1 through a6, then there's some, since a1 is greater than 1, there's some p that divides a1, where p is a prime. And so a1 times all the way through a6 is going to be divisible by p to the power of 6, right? So for example, let's say a1 equals 2, then we know since a1 divides a2, a2 is also divisible by 2, a3 is also divisible, and so on. And so the whole thing is going to be divisible by 2 to the 6th, which is not okay here. So the question is, can we get 5? And so the reason I picked 5 here is because 5 is the largest exponent. So we can never get anything more than the largest exponent. So can we get exactly the largest exponent? Well, in this case, what we could do is, if we want to get 5, we'd clearly have to distribute all the 3's across all 5 numbers. Just because, like we said, the first number cannot be divisible by 2 or by anything else other than 3. And then it turns out there are actually a lot of ways to finish this. The key thing to realize is just because a plus 1 is divisible by ai doesn't mean ai plus 1 is bigger. So we can actually keep them the same except for the last number. So we could actually just do this where we have 3, 3, 3, 3, and then the last number is just going to have all the other factors as well. And it turns out this works. This gives us the largest exponent as the length, and it also satisfies that every number is divisible by the number before it. What's the time complexity of Pollard row factorization? The time complexity is n to the 1/4, approximately. It's a randomized algorithm. There might be, let me just double check that. There might be yeah. So it's actually specifically, it's the square root of the smallest prime factor. So that's why it's n to the 1/4. And that way, in this case, it would be fine for the for 10 to the 18th. But yeah, definitely don't have to do that for this problem. That is much more advanced than is necessary here. Okay, can I explain again why the answer cannot be more than the largest exponent? So let's look at this example again. The largest exponent is 5. So let's say we found an answer that was longer than 5. So we found a sequence a1 through a6. Then since every number has to be bigger than 1, a1 is bigger than 1. So there's some prime number that divides a1, right? And then since it divides A1, it must divide A2, since A1 divides A2. And it must divide A3, and so on. So all of A1 through A6 must be a multiple of P. And so P to the sixth is, or N is divisible by P to the sixth. But that's clearly not possible here given the prime factorization. my computer is running pretty loud right now. Yeah, that's because I'm streaming and it's, processing everything. And so, yeah, the CPU is definitely running right now. Okay, and then can you explain again what the sum means in the constraint? Yeah, so basically I'm just showing why we have enough time to factor all of these numbers. The reason is because if the sum of ni is up to 10 to the 10th, then you can show that the sum of square root ni, the worst case for this is that every number is equal to 10 to the 10th over 5,000. And so this would be the worst case, which is about 7 million, which is fine in terms of runtime. The way you can prove that is just by showing that square root a plus square root b is at most 2 times the square root of their average. This is true because square root is a concave function, like it looks like this. And that way you can just repeatedly apply this inequality to like every pair of the n's until you collapse them down to 1. Yeah, so in terms of implementation, I had some like book code set up to factorize a number, but you don't need to do that in this case. You can just loop up to the square root of n basically, and then check for divisibility. And then it's just kind of the standard trick where after you loop to the square root of n, if n is still bigger than 1, then that number itself is a prime. And I guess I'll just give a quick example of that. So if we have 2 times 2 times 7 equals 28, right? We'll start from 2 and then check if 28 is divisible by 2. It is, and so we can pull out 2 squared because we keep dividing it until it's no longer divisible by 2. Then we're left with 7. So we would try 3, which doesn't work. And then 4. Actually, we wouldn't even try 3 because let me do this instead. So we'll try 3, and then that doesn't work. And then since 4 times 4 is greater than 11, we break out of our loop. And so 11 we declare as a prime, and so the factorization is that. Is it just me, or was this contest more math intensive? Yeah, I would say D is, well, it's not super math intensive. I mean, you just need to know about prime factorizations and how to find them. And then after that, it's more of a kind of a logic problem where you realize, it's just the largest exponent. And then most of these other ones were kind of more typical, just like problems on an array. But yeah, okay, so back to the implementation. Yeah, we just factorize n. We find the biggest exponent, and so that's what most is here. And then I actually just make an array where it's length most, and I also find the p that has the biggest exponent, and I just fill the array with p. And then I do what I described earlier, specifically this case. So I fill the array with p, and then I divide all of the multiples of p out of n, and just multiply the last number by that. And so just output that. And so I guess I can just run it quickly to show one example. Basically, if we had, or I can just take this number specifically. So what is this? This is like, it's kind of big. Okay, 8 times, oops, 3 times 7, so 13608. Yeah, so we would get 3, 3, 3, 3, and then 3 times 8 times 7, which should be 168, yeah. Yeah, N64T is just a kind of a more canonical way to write long And it's also nice because it's one word instead of two words. So you can actually do, for example, this, whereas, you can't do this because this is not one word when you're casting. What do I prefer for beginners? Should they use templates or code snippets or just implement it on their own in the contests? Yeah, I would say if you're a beginner, I wouldn't worry too much about templates or code snippets. You can save your code from previous problems you've done. So you can, if you remember, oh, I did this in that other problem, you can go look at that. But in general, it's good. Really, it's good to just like get practice repeating the same algorithm a few times even, just so you really like remember it in your head. And yeah, the reason I have like these different templates is because it just speeds up things and helps me, do something that I've already done like 100 times before without having to type it all again. But also in this case, I could just loop up to square root of n and that would be just fine. So it's not really a big deal. It's just like a pretty minor optimization. Where can you find the proof of this? So I think we can prove this by just squaring both sides. So wait a second. Sorry, that's not quite true. Okay, let me see. So okay, sure. We can just like go in and prove this. So that's the same as this. And so if we square both sides, we get a plus 2 times square root of ab. And it's less than equal to 2 times, plus b, a plus b. This is equivalent to 2 square root ab is less than equal to a plus b. And this is a pretty well-known inequality. This is the AM-GM inequality. So arithmetic mean greater than or equal to geometric mean. And then, yeah, again, so this one we can just prove by squaring everything. So it would just be 4ab less than equal to a squared plus 2ab plus b squared. And this is equivalent to this. But this is clearly true because it's just that. Yeah. And just quick review, the reason we prove this is because we show that the runtime of this solution is not too large. And so we can afford to factor everything. Okay, I know several people wanted to hear E and F, so we can take a look at those now. Is the inequality the wrong way? Hang on a second. No, this should be right. Right, like one example is square root 0 plus square root 4 is less than 2 times square root 2, which is true. Or are you saying a later one is incorrect here? Yeah, runtime is maximized if you split 1e10 into 5,000 equal pieces exactly. Yeah. Okay, yeah, so let's take a look at E. Okay, so we're given an undirected graph. We have n vertices and n edges. The graph is guaranteed to be connected. And it's also no self loops and multiple edges. I feel like we see this phrase a lot on Codeforces. But anyway, we need to calculate the number of simple paths of length at least 1, and paths that are reversed from each other are considered the same. So we're looking at undirected paths. And a simple path is a path that doesn't repeat a vertex. So n can be pretty large, up to 2 times 10 to the 5th. And yeah, so that's pretty much everything. Yeah, so number of simple paths of length at least 1. Doesn't that example give 2 less than equal to square root of 2? It's actually 2 less than equal to 2 times square root of 2. And this is true. Okay, so basically for this problem, the first thing that stands out is, okay, we have n vertices and n edges. So this is a very particular type of graph. It's not quite a tree because it has 1 extra edge, but it can't just be like a super highly connected graph, right? Or like, you know, it can't be anywhere close to a complete graph when n is big, right? I tried to find every path divided by 2, but there was time limit. Yeah, so that solution is intended to TLE because it's definitely at least n squared. Yeah, because it's connected, so it's definitely at least n squared. So for this problem, the first thing we should really do is try to figure out what does this graph look like, n vertices and n edges, and I have some examples set up here. So we can see that this is one example. We can see it almost looks like a tree, right? Like I was saying earlier, it's a tree with 1 extra edge, and so we're kind of thinking, okay, it seems like it's you know, it only has 1 cycle in this graph. And did I immediately know what to do for this one? So I've definitely seen this type of graph before. Actually, potentially the first time that I like solved a really important contrast problem with this type of graph was IOI 2008. There was a problem called islands where might have to, oh, here we go. Yeah, look for a bit. So yeah, we have a park with n islands, and the total number of bridges in the park is n, and so we get this exact type of graph. The problem actually asks you to compute like the sum of diameters of every component, but and then n is up to 1 million. So yeah, I've definitely seen this type of graph before. Pretty familiar with it. So I kind of already knew what the graph looks like for this problem, but just to kind of do it from scratch. Yeah, so we suspect that it's a graph with exactly 1 cycle. How do I remember that from 12 years ago? Yeah, that was my first IOI, so I definitely remember that. So, and I just looked at it earlier today after the contest. So that's why I like had it kind of ready to find. So yeah, so we can actually prove that the graph indeed only has 1 cycle. The way we can do that is, so we have a connected graph, right? And I can't remember problems from 12 days ago. So we have a connected graph. So what that means is we can find a spanning tree, any spanning tree. It doesn't have to be the minimum. There is no minimum here really because every edge is the same weight. So let's take one example of a spanning tree. And so, you know, a tree has n vertices and n minus 1 edges. So we just actually removed 1 edge. And so we're just adding 1 more edge here. So for example, in this case, we added 3 to 8, and that creates a cycle along the path in the tree from 3 to 8, right? And so more generally speaking, the graph looks like a single cycle with a bunch of trees at each node. So every node of the cycle is actually its own tree. So in this case, we can, if we delete the cycle edges, it'll look like that, just a bunch of different trees, right? So now that we know that the graph looks like this, we can think about, okay, how do we know, let's just like think about a pair A and B. How many simple paths are there from A to B? So there's 2 cases. One case is A and B are in the same tree. So yeah, let's just remove the cycle edges for now. Let's think about 12 and 14, right? So there is this one tree path from 12 to 14 because any two vertices in the same tree have one path. And then if we wanted to use cycle edges, we would end up including 4 in our path twice. So we actually can't. So for any pair in the same tree, there's exactly one path. And then if we have a pair in different trees, so for example, let's look at 12 and 8, then we do have to go into the cycle. So we have to go straight up to our tree root from both vertices. And then we have two choices in the cycle for how to cross. So we can go 12, 10, 4, 3, 2, 7, 8, or we can go 12, 10, 4, 5, 1, 2, 7, 8. So for any pair not in the same tree, there's two ways. So actually, all we need to do then is just figure out the sizes of each tree, because the sizes of each tree will just tell us how many paths there are. And so there are a couple ways to do this. The way I did it in contest was this is my copy-pasted code. I used union find to figure out which of the edges creates a cycle, and then skip that edge. I actually created the tree with the rest of the edges, and then using that edge, I find the path through that last edge's two vertices, A and B. So in this case, for the 3 and 8, I would find the path 3, 5, 1, 8 in the tree. And then that's my cycle. And so then I find all the cycle edges, and then I do union find again, except I skip all the cycle edges, and that gets me the sizes of the trees. And so then to compute the answer, it just looks like n times n minus 1, which is n choose 2 times 2, and then we subtract the number of pairs within the same tree. So that would just be size choose 2 for every subtree, or for every tree. Wow, that website's really cool. Yeah, this is CS Academy's graph editor. It's a pretty nice one for just, if you want to visualize sample data or you want to kind of mess with some different examples. They have a couple different things here. You can click on a node and it will stay in place. You can drag nodes around and rearrange them. And a couple different things here. So yeah, check that out. I'll put the link in the chat. Yes, I will upload the stream to YouTube afterward. And then there's another way to do E, which is maybe a little simpler, where you still use union find, but to find the cycle, you can actually just use DFS. And so the way we're going to do that is we're just going to start from any nodes. We just start from 0. We just go around, and then once we visit the same node twice, we look at our DFS stack and then pop that until we see the same node again, and that's our cycle. And so the implementation looks like this. If we visited the node again, then we start building our cycle. We just put everything from the back of our cycle, or back of our stack, into the cycle, and then we return. Otherwise, we push our current node on the cycle, we mark it as visited, and then we go to every neighbor that's not the parent. So it's important not to backtrack your edge, otherwise you'll find a cycle of size 2. Yeah, so pretty simple, find the cycle, and then same thing as the other solution, just put all of the cycle edges into a set, union find, unite all the edges that are not cycle edges, and then we get all the sizes again. So what I'm doing here that gives me the hovering, or the, it also gives me something cool, which is just errors. So if I type, XYZ, which is not in my code, it will give me error use of undeclared identifier. And this is set up via, this is something that Eknerwala told me about actually. It uses something called LSP, and then also uses the compiler clang-d. That's spelled like that. And yeah, if you set those up together, then you can get these live errors and so on, which is pretty nice because you might make some sort of mistake, and then it'll just tell you right away. So for example, if you do I equals 0, I less than n, and then you do j plus plus, you'll get an error. Well, I guess I don't have n, but like that. You'll get an error right away, and so it'll catch it for you. Can you do it without union find? Yeah, you can totally do it without union find. You just, instead of using union find to find the tree sizes, you can just use DFS again to find the tree sizes, just like finding connected components. The reason I use union find is because it just feels super easy to use. I guess, once you already have this code, the code is even like really not that long either. But I just paste in this code, and then it's like really nice interface. I just initialize with n, unite some edges, and then I have all the sizes this way. Where did I get the graph? So I put it up earlier in the chat, but I'll just put it in again. This is CS Academy's graph editor, and yeah, all you have to do is put in these edges, and it'll give you something like this, which is pretty nice. Oh, the specific graph. Yeah, I just made this up as an example. How does the n choose 2 part work again? Yeah, so I guess I can go into more detail quickly about that. So let's say, for example, we have 3 components, or 4 components where the sizes are 1, 2, 3, 4. Or maybe I'll just make it 1, 2, 3, 7, so it's not all sequential. And we want to find out how many paths there are. So one thing we can do is we could do like 1 choose 2 plus 2 choose 2 plus 3 choose 2 plus 7 choose 2, and then we can also add 1 times 2 plus 1 times 3 plus 1 times 7, and then 2 times all this plus 2 times 7, right? Like, that was pretty complicated. And then in fact, if we actually did a loop and did this, this would be n squared, so that's not even okay here. You can improve this with like, prefix sums or whatever. But an easier way to think about it is, let's just count 2 times n choose 2. So every pair, we're counting them as having 2 paths. But actually that's not right, because some of them only have 1 path. The ones that only have 1 path are the ones in the same tree. So now we can just subtract out everything in the same tree. And so this is a lot easier, and that's what we're doing here. So this is 2 times n choose 2, and then we're just subtracting size choose 2. Okay, so one last problem, problem F. Please share. Oh, I have gotten people asking about my file that downloads and runs the samples. Yeah, I have a couple different scripts for this. I'm not sure if it's like not super easy right now to share, but maybe I'll share it at some point later. We'll see. Anand didn't realize that it was n edges. He thought it was n vertices and m edges. Yeah, I think I think the more general version of this problem is pretty like NP hard, I would say. Dark Coder, you said dry run, please. What do you mean? Can you dry run one example? Oh, do you mean for E? Sure, we could look at like this, for example. Let me try to fix this cycle. Okay, this is funny. Okay, there we go. Yeah, so for this example, we have the cycle here, and then we have 4 components, or 4 trees. we have sizes of 3, and then 3, and then 1, and then 1, right? So in that case, this is what we're doing here. And so we just do, overall n is 8. So we just do that, and then subtract 3 choose 2, 3 choose 2, 1 choose 2, and 1 choose 2. And so that would give us our answer. Their certificate expired today. I don't seem to have any issues for some reason, but that is funny. Hopefully they fix it. Maybe someone will see the stream at some point. Someone from CS Academy? I don't know. We'll see. Where can I find earlier codes that I explained? So if you check out the videos tab of my channel, you can actually find the current video. And let me paste the link here. So if you go there, you can find the current video and you can rewind and rewatch a part if you're confused about something. Okay, so let's take a look at problem F. This is the last problem. So here we have an array A consisting of n integers. And we want to find a way to split up the array into 3 consecutive subarrays where the max of the first subarray equals the min of the second equals the max of the third. And we just need to find any partition. And the key constraints are n is up to 2 times 10 to the 5th, and the AI are anywhere between 1 and 10 to the 9th. It looks like we were getting an editor debate already. I thought the classic debate was Vim versus Emacs, right? But it looks like the 2020 level of this is Sublime versus VS Code. Okay. Anyway, so yeah, it's really easy to get a polynomial time solution to this problem, right? A too slow solution, which would be just loop over all the choices for x, y, and z, and then just check if it works, right? And so there are actually only n squared choices, so we can think of it, instead of x, y, z, we can think of it as just picking 2 cutoff points, a and b. And so everything between 0 and a is the left, between a and b is the middle, and then between b and n is the end, or the last one. And then checking the mins and maxes would be n times, so that's n cubed. One thing we can do is we can use RMQ, also known as range minimum query. So this is an algorithm where you have an array, a fixed array, it doesn't change, and you want to query, for subarrays from L to R, you have a bunch of queries that look like L and R. You want to query what is the, for example, what's the minimum value in this array, which would be what, right? Or this subarray. And so there are a bunch of different solutions for this. The most classic one is to use what's known as a sparse table. Basically, you compute for every power of 2. So for every power of 2, you compute the minimum of the subarray, or of every subarray of that length. So for example, let me just say this, if we have an array, then we would compute, for the length 1, what's the min of every subarray, which is just the array itself. For length 2, what's the min? So starting from 7, the min would be 6 because it's 7 and 6. Starting from 6, it would be 6 again because it's 6 and 8. Then here would be 2, and then here would be 2. And we don't have we don't have a fifth element because it's only subarrays of length 2. And then we do the same for length 4, which would just be 2 and 2. And so now what we can do is, given an arbitrary range L to R, we can break it up into 2 segments that potentially overlap. So for example, let's say we want to query the segment from like 5 to 10, right? Then we could do the segment 5 to 8 and the segment 7 to 10, right? And together these cover the segment 5 to 10. And notice both these are powers of 2 in length. So we find the largest power of 2 that is at most the length, and we can just query this with 2 segments. So this is n log n pre-computation and n log n space, and then O of 1 query. I would recommend reviewing this page if you want more details. But anyway, just going to assume that we have RMQ now. And so that helps optimize the solution I described to n squared, because now it's O of 1 to check this. Okay, so the next thing let's do, let's first pre-compute the prefix maxes and the suffix maxes, because that is what we need for 1 through x, and then also the third subarray. And now, earlier I was mentioning we cut the array at 2 points a and b. So what I did is actually let's loop over b. Given b is the start of the last array. So given b, we know the suffix max for b. So we know what this value needs to be, right? And so based on that, we can figure out kind of a range, or exactly a range that x needs to be. Because if we think about the prefix maxes, they never decrease, they can only increase. So the prefix maxes might look like, negative infinity, 3, 3, 3, 7, 7, 8, 10, 10, right? And so if we know what number we want, for example, 7, there's a certain range that x is allowed to be. And so we know what b is, we know the value, we know the range that x is able to be. Now we want to figure out, are any of those x's, do any of them work for setting up the min of the second array to be the right value? And here we can use the same logic that we used on the prefixes with x. Basically, let's say okay, maybe I'll just make my own array. So let me see. So okay, so let's say we put b here. So we have a max for the suffix of 2. Let's say we're solving, b equals the second last element. And then we need the prefix to have a max of 2. So that means the prefix can end here, or we can end here, or here, or here, but we can't go past the 3, right? And so basically we have a bunch of choices for our middle array. The choices are 3, 2, 2, 3, 2, 1, 2, 3, 2, 1, 1, 2, 3, 2, and that's it. So basically I should actually set up like this because they should be right aligned, right? And basically we have a fixed endpoint for the middle of the array, but the start point can vary, right? And the key observation is that if we start from here and we push the start point toward the left, because we're taking the min of this array, the min for each of the start points can only go down. It can't go up again. And so again, we have this like essentially sorted list of potential minimums for our middle array if we have a fixed endpoint and we're figuring out which start point we want, right? So we can actually binary search this list to figure out what is the best start point to get exactly the value we want. The thing is, we don't actually have the array here because in order to build that array, it would take n squared time because we have to take for every start and every end, what is the minimum, right? But that's where RMQ comes in. And so here, this is basically what we're doing. We're doing this binary search, and we're using RMQ along the way to figure out what is the minimum. So we take the suffix max for B. Start and end are the range that X can be. And then we were just binary searching between those 2 points to figure out where do we get the right RMQ value for the middle array. And then if we get a valid solution where the RMQ gives us exactly the same value, then we get our answer. Okay, so a little bit slightly complicated there. We need to like make a couple observations. Does that part make sense to everyone? Are there parts that are confusing? Problem C discussion is completed. You can check out the videos part of the channel in order to go back and watch that. Yeah, makes sense. Okay, nice. Can we use segment tree? So yes, we can use segment tree. The key thing here is that RMQ is O(n) log n pre-computation. I guess I can just remove the O. It's exactly n log n, and then it's O of 1 query. Segment tree would be n pre-computation and O of log n query, right? And so in this case, because we are doing basically n log n RMQ queries, if we use the sparse table, then our overall runtime is n log n. If you use the seg tree, then it's n log squared n, because we have n log n queries that each take log n time. So B equals like n minus z here. We will take the first position with the same maximum value as the suffix maximum because minimum won't be affected by the max value. So that's not quite right. So we know the suffix, we know the suffix maximum, and then based on this value, we want this value to match all 3 of these, right? For the prefix maxes, we can just do a binary search and find the range of prefixes that get you this value. And then within that range of prefixes, we need to figure out, is there any one of them that gives us the right minimum for the middle array? And then that's where we do another binary search and the RMQ comes in. Isn't it right to take last or pre-last value of suffix max and prefix max? I'm not sure exactly what you mean by that. So we can have arrays where, for example, the prefix max matches for a very early prefix and the suffix matches for a very late suffix, or vice versa. Like these can be anywhere within the array, so we don't actually want to pick any specific one. Could I take a look at Zhang Li's solution for F? Yeah, I can take a look in a sec. Anand said I had a slightly different solution. Oh, so try each possible value for the common element and then increase X and Z as much as possible. Okay, so this is because Okay, so that mostly makes sense. If you pick a certain value, then you kind of want the prefix and the suffix to be as long as possible, so that the minimum doesn't go too low. But you do need to make sure that you do include the value at some point in the middle array. So how do you handle that? Sleepish EP says iterating. How about iterating from highest to smallest and maintaining an LR range from minimum middle? Uh, oh, I see that. Okay, that makes some sense. Yeah, so basically you would want to avoid, um, or any numbers bigger than your current number, you would need to, are like forced to be in the middle. Um, yeah, I think both of these solutions, the general idea also works. It sounds like you have to be a little careful with making sure you include the actual value itself. Oh yeah, Anand says you only have to check plus or minus 1 because if you miss the value, then it should be at the very end of the prefix or suffix. Yeah, that makes sense. Okay, yeah, we can take a look at Janley's solution. Oh, here we go. Okay, so this is prefix and suffix max. Okay, so his R is the same as our B, and the stack keeps track of the prefix minima. Oh, so wait, sorry, that's not right. Oh, it's the minima from R toward the left. Oh yeah, Anand, so you can actually, it turns out you can actually do RMQ in O of n preprocessing and O of 1 query. So maybe that gives you an O of n solution, given what you're saying. But I will say that the O of n and O of 1 is super impractical, and it involves some crazy partition tree precomputation that doesn't actually end up being super worth it. In practice, the sparse table is generally the solution that I use. Okay, I think I'm piecing together some of what he's doing here. So R is the start point of the third subarray, and then we have a stack that tells us all the indices where the middle subarray would decrease, and oh, okay, I think that makes sense. Yeah. So yeah, we're just searching the prefix maxes, and then also the minimum in our or minima in our stack, and we're just trying to figure out if they overlap. Yeah, that makes sense. And so it's pretty much the same idea. You actually it's almost exactly the same idea actually. You just don't have to do RMQ because you're not querying just like arbitrary subarrays in random order. You're querying with the right end of your subarray increasing, and so you can actually build the RMQ using a stack instead. Where in this case, yeah, it's like a general query would take login time, but since he's doing just a binary search on the stack, it's also login time. Yeah. Is sparse table faster for n up to 10 to the 9th? So it's not that the it's actually not that the O of n is slower in practice. It's not slower in practice to build. It is slower in practice to query because instead of the clean sparse table where we just do 2 memory accesses, we have to like cut up everything into blocks and then find the minimum over the blocks and then find the minimum within the blocks and so on. So it's like at least 4 or 5 memory accesses. And so query time is worse in constant factor. And the thing is just that the n log n pre-computation is super fast. Like it's super cache efficient because we're just iterating in order over and over. So this is almost never a problem for runtime. Like even for n equals 1 million, I think this still runs super fast. The only reason you might want to do the O of n RMQ is to improve the memory if you're worried about MOE. But otherwise, generally the time that you care the most about is the query time. And so this is, the fastest query time you're going to get. There was a discussion, I think second thread asked a while ago about RMQ, and then there's a discussion where Saketh chimed in and explained some of this. Let me see if I can find it. Yeah, okay, I found it. So second thread was asking about the RMQ and O of n pre-computation and O of 1 query. And then asked about this. And then basically Saketh said, you can do it, but the time difference is not that big. But you do get some memory improvements. Again, yeah, the query is usually more of what you're optimizing for. And the O of n version takes more. And just some like specific tips if you really want to implement the O of n version. Yeah, I actually do have a version of RMQ that which one? I guess it's this one. Yeah, okay. So I have one that it's actually what JCG was describing here, where you store bit masks of the blocks. It's like a clever idea he mentioned here. But yeah, basically I just have like a fixed block size of 8, and so this reduces the memory by about 8x. It's a little worse than that because there's still a bunch of O of n arrays. So yeah, so I do have this code. I almost never use it though because the query time is more important. Hi, Afterjack. Glad to have you here. This is your first round, so awesome. Yeah, I'm glad you're learning a lot. Okay, yeah, so that's pretty much it for this round. Covered everything here. Did anyone have any further questions about any of the problems? How do I feel solving A and B of div 3? I mean, it's fine. It doesn't take too long, so it's not a big deal. I think I spent like 2 minutes on both of them. Um, so I won't go over the whole problem again, but if there's something specific that I said that you might be confused about, let me know, and I can explain that. If you want to just hear the whole problem again, then um, you can go into the video section of my channel and you can find this current video and just kind of scroll back. Can I hack people on stream? Yeah, that would be pretty funny. I don't know if there's anything that seems super hackable here. And I probably do have to run soon, so maybe not this time. I think it would be pretty educational. Yeah, I think that's a good idea. Maybe I'll do it on a future round. After Jack, I will also subscribe. I can't get subscribers right now because I'm still relatively new on Twitch, but you can follow me and that way you can get notified when I have future streams. I think eventually if I do enough streams, I can get subscribers. So that will be fun. Can I talk about problem D? Yeah, so again, is there anything specific in the previous explanation that you want more details on? Because otherwise you can just check out the video. But if you have a specific question, let me know. Okay, yeah. So I'm getting a lot of requests to just explain the same question again. So I won't do that, but Meyer is asking, how did I think of the solution for D? So yeah, so for D, basically the key thing is, so we know that each AI is strictly greater than 1, and then they multiply to n, and then AI plus 1 is divisible by AI, right? And so it's nice to think about the prime factorization. And if we look at these constraints, we can find that we can indeed factorize all the numbers in time. And then once we know that, we can just start from a prime factorization instead to solve the problem. And really, if you just work out a few examples, like, what was the one? The one I did here, like 2 cubed times 3 to the 5th times 7, you can find out pretty quickly that you can do 5 and you can't do 6. And 5 specifically is the biggest exponent. And so you can just think about a couple examples, generalize from there, and then find the solution. CX Mill says, why did you take my first place at CodeChef Div 2? So that honestly was the first CodeChef that I've done in like 10 years or something. But, oh, so are you Pseuda, P-S-E-U-D-A? That's super funny. Yeah, that was actually, that round was actually pretty nice. I was definitely pretty frustrated when they just suddenly, they literally added a new problem 50 minutes, like almost an hour after the contest started. And I think Tadija Sabez was actually in second with all the problems except that one. I think he actually just left. I think he didn't realize there was a new problem. And so, I guess in that sense, you know, getting second place ahead of him is also nice. That's right, Urtra. I'm actually a 4-star coder now after that contest, so moving up. Dev Park, you can check out the Twitch video, and that way you can just find my explanation for E. Here's the link for that. It'll be the first video in there. Yeah, that's right, Urtra. You better bow down to this 4-star coder. Anyway, okay, sounds good. I gotta get running, but thanks everyone for coming. I will post these on YouTube. But yeah, this was fun. Hope to see everyone next time.